last talk, we ended up with the Minkowski inequality, and we showed that that holds for arbitrary filtrations, but fails but can fail arbitrary filtrations. So this was first proven by Teissier and Rees and Sharp in all in dimension 2, and then finally by Dan Katz in all dimensions. So you suppose that R is a d-dimensional, formally equidimensional local ring, and I1 and I2 are M primary ideals. Then the following are equivalent. The first statement is that the Minkowski equality, which is the multiplicity of the product of the ideals I1 and I2, take the d through to that, is equal to the sum of the d roots of the multiplicities of I1 and I2. Okay, and remember that this is always an inequality, but this is that we have some nice statements when it's actually an equality. The second statement is that, in fact, I'm going to do like I did last time. I'm going to write down the third statement, which is what they actually proved, is that there exist positive integers A and B such that I1 to the A integral closure is equal to I2 to the B integral closure. Okay, so since we're generalizing this to filtrations, this statement cannot generalize, but 3 is equivalent to this statement, that there exist positive integers A and B such that the integral closure of the R algebra summation I1 to the AN Tn is the integral closure of the R algebra summation I2 raised to the Bn Tn. Okay, 2 and 3 are equivalent. So in this statement that you don't need the formally equidimensional assumption for 3 implies 1, and this is quite a bit easier to prove. It's true with no assumptions, as is 3 equivalent. Maybe I should say that these are true with no assumptions. On formally being formally equidimensional. Okay, so that's their theorem. So the question here is that let's suppose that I1 and I2 are M filtrations. And then you can ask, do the following holds? The first statement is that the Minkowski equality E of I1, I2, 1 to the d is equal to E I1 dth root plus E I2, 1 over d. Okay, so what is this? This is the filtration, which is I1m, I2m, where you just multiply each of the degree m terms in the filtrations. Okay, and then the second statement is that there exist positive integers a and b such that these algebras have the same integral closure. Okay, so that's the, are these things equivalent? Okay, so we look at this, and just like we saw in the Rees theorem, that the 3, or in fact 2 implies 1, is true quite generally. The 2 implies 1 is, it's the same thing over here. 2 implies 1 is true quite generally. So one can say that 2 implies 1 is true for arbitrary M filtrations. The only thing we need is that this dimension of the nil radical of r hat less than d condition. We need that for the limits to even exist. But we do have that 1 implies 2 is false for arbitrary M filtrations. And in fact, this is from this paper of mine with Brengema and Hema. Okay, so that the counterexample, in fact, I don't know if I gave the counterexample for the Rees example, but the same example works here. It's a very simple counterexample, and it's somewhat illustrative of the kind of problems which fail. If you just take R to be a regular local ring, and you take I1 is equal to all powers of the maximal ideal, and I2 is equal to n plus 1 power of the maximal ideal. They satisfy 1, they have the same multiplicity, but 2 doesn't hold for any A, B, and Z. Okay, the problem is that for I2, if you never quite get to that nth power, but at infinity you do. So that's why you have the same multiplicity, but you can't get the integral closure as the same because of this. Okay, so quite simply, this fails. Okay, so remember, like last time we did the Rees ring, we also found, in fact, the same example gives a counterexample to the Rees theorem. So this over here now gives, we found though that for the Rees theorem, that if you assume that one is contained in the other, one filtration is contained in the another, and they have the same multiplicity, then they have the same integral closure. That holds for bounded filtrations. Okay, and the exact same thing happens here. So this is what, in fact, that's what I've done this summer, basically, which is This is the Teissier, Rees, and Sharp, Katz theorem for bounded filtrations. Okay, so in fact, we need this. Well, these are the assumptions that I can get it in at this point. I suppose that R is a d-dimensional, analytically irreducible or excellent local domain, and I1 and I2 are bounded M filtrations. Then the following are equivalent. The first statement is, well, the Minkowski inequality, or should it say equality, E of I1 times I2 dth root is equal to E of I1 dth root plus E of I2 dth root. And of course, the second statement is that there exist positive integers A and B such that there is equality of integral closures. I2 Bn Tn. So we have this of course, in the ring R of T. Okay, so this theorem I proved about a year ago in dimension 2, but I used a lot of special things for dimension 2. I used theory of Zariski decomposition, the fact that the intersection matrix of exceptional divisors is negative definite. And these things don't generalize terribly well to higher dimensions. So I wasn't really sure if this was going to work. I was really pleasantly surprised that it actually goes through. Okay, so let me fill in the canvas of this theorem a little bit. Okay, so let's let R be a d-dimensional, for now on, R will be a d-dimensional normal excellent local domain. This is the essential case. Also, I see that I should have reminded you what is a bounded filtration. So let me go back and backtrack and do that from last time. There's a concept of divisorial filtrations. Is a filtration. That means something else. A bounded filtration I is equal to I sub n is a filtration is an M filtration such that there exists a divisorial filtration ID equals IMD. Such that the integral closure of IN is equal to the integral is actually equal to this. So remember, for a divisorial filtration, it's always integrally closed. Okay, so now I'll also remind you of what a divisorial filtration is. So now I will give this this assumption. Let's let R be a d-dimensional normal excellent local domain. And to start out with, let's take I to be just an M filtration. Now let's let U, mu, be an N filtration, an M valuation. And then let's let tau mu M of I is equal to mu of IM, which is just equal to the minimum of the values mu of F, such that F is in I sub M. And of course, that's a positive integer. Okay, now we define gamma mu I is equal to the infimum over M of tau mu M I over M. That infimum you define. And now this is going to be an important invariant we'll use. Now let's look at divisorial filtrations. Okay, so let's refresh our memory about this. So we find a representation of this. So we let phi from x to spec of r be the blow-up of an M primary ideal with prime exceptional divisors. E1 out to ER, such that X is normal. We can always do that since we're starting with a normal R, which is excellent. D is equal to A1 E1 plus AR ER is a representation of I of D. Okay, so remember, this is all it means to be a representation. You can define I of D just strictly in terms of these intersecting valuation ideals, but then you can get there exists a geometric realization of this type. Okay, so now let's take nu sub E sub I be the M valuation with valuation ring O XCI. Okay, so remember we defined this gamma, which is up here, that we take for each IMD, you take the minimum value of an element in it, and then you take the infimum divided by M. So somehow this represents somehow asymptotic M times gamma represent somehow asymptotically what the order is of the value of order of the filtration. Okay, so we have this important inequality that gamma EID is always bigger than equal to AI for all I. That's the way it's defined. And if I take X to be the roundup of a real number X, using this ceiling, the gamma X of OX minus the sections, well, I guess if I define things correctly, I can define this for any real divisor. But what I do is I take the roundup. Now, this is what this means is I round up the coefficients. Now, it turns out that this gamma EID can be an irrational number. So one has to do something with this. And what does this mean? These are viewing these sheaves as these are reflexive rank 1 sheaves. They're not necessary. If this divisor isn't Cartier, which is entirely possible because we don't know if resolution of singularities is possible. But this exists in the sense of...
Excuse me, Dale?
Yeah.
Looks like the screen is frozen.
Okay, yeah, thanks for saying something. Can you see it now?
Yes. Yeah.
Okay, I think I'm going to have to watch this. The screensaver went on, but I'm about halfway through it. Hopefully it just came on.
Yeah.
Okay, so, all right, so the point is that this is, in fact, since we're in a normal variety, a normal ring, this is just I of MD for all M in N. Okay, so this gives us a geometric method of computing this thing. And in fact, I was mentioning that there were many different representations for this filtration. And at least on the variety of X, this is somehow the best one. In fact, this IMD is actually equal to just this. I should have written this line in right here. If I start out with the original divisor. Okay, that's I of MD, and this always holds. So what does this mean here? That this is essentially the definition over here, the second one. This is the definition, and this is always true from this. But then one has this better way of writing it, or this tighter way of writing it. So what this means here is that M times A sub I is the prescribed order of vanishing of elements of I of MD along EI. Okay, that's what we've asked for, that we ask that it vanishes up to that order. That's what this information about the value being bigger than equal to MAI means. But on the other hand, M gamma EID is asymptotically the actual order of vanishing along EI. Of course, for instance, if this gamma EI is an irrational number, maybe you'll never actually realize it, but it'll get closer and closer as you go to infinity, in the sense that this gamma ID and then the order of IM over M, the difference goes to 0 as M goes to infinity. Okay, so maybe I should even write this out. Gamma EID can be an irrational number if D is bigger than 2. So this is another thing that's nicer in dimension D equals 2. Okay, so this theorem follows from this, which I'll call theorem F, where we suppose that R is a d-dimensional normal and excellent local domain. Let I of D1 and I of D2 be divisorial M filtrations. And then let's look at X to spec R. We can choose this to be a common representation of both filtrations. Of D1 is summation I equals 1 to R alpha I EI, and D2 is summation I is equal to 1 to R beta I EI. So both of these are realized as divisors on X. Then the ID1 and ID2 satisfy the Minkowski equality. If and only if the following condition holds, that the ratios gamma EI D2 over gamma EI D1 is equal to the ratio of EI D2 1 over D EI D1 1 over D is equal to AB, an element of Q, where here we have for some AB in positive integer. That's what it means to be in Q. And this is for all divisors. Okay, so this holds if and this happens. Now, you see the way I've written it, I've made some assumptions, obviously, about things being positive. It turns out that these numbers are always positive. The gamma E sub i's and the multiplicities for divisorial filtrations. For arbitrary filtrations, the multiplicity could be 0. And another thing which is going to come up later, or maybe it's more buried in the proof, is that the mixed multiplicities of filtrations are always positive. And this follows from a theorem of Hema and Jugal, Verma, and myself, where we show that if something's an analytically irreducible local ring, local domain, then and the multiplicities are positive, then all the mixed multiplicities are also positive. Okay, so we needn't worry about this issue. Okay, now this is the first half of it, but I think I've already tried to convey a little bit about being nervous about irrationality in this. You can see the gamma E sub i's and the multiplicities can all be irrational numbers. So somehow this seems, I was a bit worried about this. And in fact, this part I showed, and it took me a little bit longer, and I thought it maybe wouldn't even be true, but it turns out that when this happens, that these guys always are these guys. In fact, I wrote the wrong thing. Sorry, I jumped the line here. This should be this statement here. I jumped the line, so I'm sorry about this. Somehow it's too early in the morning for me. What I should have written was this. I'm writing the wrong condition here. Okay, so let me go back then. That this is the condition which Minkowski is equivalent to these ratios of multiplicities being the same for all of these actual measures of vanishing, these gamma sub e sub I. So somehow you get some sort of a virtual real divisors from these guys, which determines what the filtrations are. And the Minkowski equality holding is equivalent to these guys being the same. Okay, or their ratios being the same. Okay, so now let's move on to the second thing. When this happens, then I have what I mistakenly wrote before. It's in fact a positive rational number where A, B, R, and Z for all of these guys. So in fact, you get more. And in fact, getting the fact that these are all equal to this ratios of multiplicities is not so difficult from this one. But getting that it's a rational number was a bit tricky. So I'm not going to go into that, but it's actually, there's some generalization of the so-called asymptotic Samuel function, which works to show this. Okay, so once we know this, we can easily see now why we get this, in fact, equality of the filtrations when you multiply by A and B. So remember, this was summation I equals 1 to R, M A gamma EI D1 EI. And this is equal to, we go back and we look at these equalities here. And from this, this line right here, in fact, we see that this is exactly equal to this one. B gamma, this should be a 1, gamma EI D2 EI. And we saw before that that's equal to IBM D2 for all M and N. So this establishes the quality of filtrations, but in fact, one reduces to bounded filtration. So one can, for instance, recover the classical resultant for this and for powers of ideals. And in that case, you get the integral closures of filtration statements. So in fact, since these filtrations are integrally closed, they're actually equal. Okay, this is the essential case for proving the theorem. Okay, so now let me give an outline of the proof of the first statement. Okay, this is, I think, the most interesting statement. This equivalence here. So this will be an outline of proof of first statement. Of theorem F. Okay, so let's define this function over here, f of n1, n2. It's a limit as m goes to infinity of the length of R mod I m n1 d1 times I m n2 d2 over m to the d. So this is the thing which we've been looking at, which allows us to define the mixed multiplicities of filtrations. Now the Minkowski equality, if you use this and you also remember that the other Minkowski inequalities exists, you have these other inequalities in the coefficients, that this tells you then that you can write it in this very simple form. It's power of a linear function. Okay, where here you following the classical language, the E naught is the multiplicity of D1, and ED is multiplicity of ID2. Okay, so this has this nice form. So we need to remember this has this nice form. Okay, so now let's take mu to be any M filtration. Okay, so then, and let's let nu from the ring R to ZD, or in fact, it's evaluation on the quotient field, which dominates R, such that V is equal to mu, and then something else. A technical word for this is that nu is composite with mu. So now we define gamma n1, n2 is the semi-group of nu of fm, pairs nu of fm, such that f is in I m n1 d1 times I m n2 d2, and this sits inside of nd plus 1. And then I define delta n1 n2 equals the intersection in R d plus 1 of the closure in the Euclidean topology of the real cone generated by gamma n1 n2, where you cut with level 1s. So you intersect it with RD cross 1. Okay, and then we also define this for the ring R, where you just set n1, n2 equals 0 and use this definition. Okay, so if you take this, okay, so we have a theorem which allows us to compute multiplicities. So if there exists a positive real numbers such that letting h phi n1 n2 be equal to x1 xd in Rd such that x1 plus xd is less than or equal to 5 e naught 1 to the d n 1 plus phi e sub d 1 to the d n 2. Okay, so I might say something is you notice that these that this half space looks kind of like that. So this was carefully chosen so that these to match. That plays a role in everything working out. Okay, and then we have delta phi n1 n2. We define this to be delta n1 n2 intersection h phi n1 n2 with this half space n1 n2 tilde of this I define to be delta of r intersection h phi n1 n2 with the half space. Okay, so we do this to get these deltas are closed and convex, but they're not compact. So for what we're doing, we need to have something compact. And also, we need to be able to compute the multiplicities from this. So we have, in fact, that f of n1, n2 is the delta, some constant delta, times delta phi of n1, n2 minus the volume of the compact convex set delta phi n1, n2 for all n1, n2 in n. So remember, f of n1, 2 is this function which measures the length of R mod I n1 d1 plus n2 d2 times I n2 d2. And I can tell you what delta is. That is the index of the residue field extension of R mod MR in the valuation ring. Okay, so there's some commutative algebra in this, so I'll mention that. This, for instance, this uses the Izumi's theorem, Rees's form of Izumi's theorem in order to get this. The problem is that you need to get it so that when you cut, everything beyond this H, where the H phi N1, N2 cuts, that these two guys have to be the same. So that's a boundedness type of problem, and this required some linear algebra. Now, let me say a little bit about this theorem, in particular about the method. That this delta phi n1 and n2 and delta phi n1 n2 are intersection which the H minus are compact convex subsets of Rd. And the proof uses the method of computing asymptotic vector space dimensions of graded families using Akunkov bodies, which was developed by Akunkov and Lazarfeld and Mustada and Kovansky. This Lazarfeld and Mustada paper, as I mentioned at the beginning of the last talk, was really inspired me to get going on this whole line of investigation. And I should mention that to me, this method is very reminiscent of Minkowski's geometric techniques in number theory. Okay, so this is now we've converted everything into a problem in convex geometry. Okay, so now what we need to do is go back and look at things a little more closely. Okay, so let's look at delta R. This is the region, the closed convex region, which you get from looking at the whole ring, not the filtration. So this is in fact a closed convex cone with vertex at the origin. Okay, you get the origin by nu of 1 is equal to 0. That isn't, you don't have any units in it in any other, in an M primary ideal, so you don't get 1 in the delta phi n1, n2. Okay, so this implies that you can actually compute the volume.
Hello, Dale. Can you refresh the screen?
Yeah, thank you. Okay, okay, you've got it there. Okay, this guy over here is this compact region. You see, hopefully not too much was lost. Okay, this is equal to, you can compute E naught 1 to the D plus N2 ED1 over D raised to the D power times phi to the D times another constant, which you cut at 1. Okay, so the point is that this is a constant times this nice power of a linear thing. So what this allows us to then is we can define a new function, Hn1, N2. This is equal to the volume of delta phi N1, N2 and then going back to that that theorem describing f of n1, n2, minus f of n1, n2. Now I divided by delta times d factorial. This is equal to some constant times e naught 1 to the d n1 plus e to the d n, the dth root of e to the d times n2 d power. Okay, so this function which computes the volume of this strange region, which you get from the filtration, actually has this nice form. Okay, so now let's let G n1, n2 be the volume of n1 delta phi 1, 0 plus n2 delta phi 0, 1. Now this is in fact a homogeneous real polynomial of degree d. This is a theorem from convex geometry. This n1 delta phi 1, 0 plus n2 delta phi 0, 1 is the Minkowski sum of these guys, of these compact convex sets. And this is a classical theorem that this was maybe due to Minkowski, but certainly it was known by him. And I should mention that the coefficients of G are called mixed volumes. Now, if we go back to what we had here, is that n1 delta phi 1, 0 plus n2 delta phi 0, 1 is always contained in delta phi n1, n2. One has this. So this implies that G of n1, n2 is less than or equal to h of n1, n2. H measures the volume of the second guy, and this over here, n1 delta phi 1, 0 plus n2 delta phi 0, 1 measures G measures the volume of that. Okay, so now this is where we go back and we study the information we have a little bit more, that we know that G of 1, 1 is equal to h1, 0, which is bigger than 0, and G0, 1 is h0, 1, which is bigger than 0. So for 0, t between 0 and 1, we compare these functions, h of 1 minus t, t1 to the d, is equal to 1 minus t, h1, 0, 1 to the d, plus t, h0, 1, 1 to the d. Well, we check this just by going back to that nice expression h has and verifying directly that this works. Okay, now we know from these inequalities right here, we know that this is equal to 1 minus G of 1, 0, 1 dth root, plus t, G0, 1 dth root. And now this is less than or equal to G minus 1 t, t1 to the d. And this is the so-called, the famous Minkowski inequality of convex geometry. Okay, so, and this we know from, as we observed above, that this is always less than or equal to h of 1 minus t, t1 to the d. So we see that we have inequality. We started with h of 1 minus t, t dth root, and then we ended with it. So we have equality in the Minkowski inequality. Okay, well, there's another part of the theorem that the Minkowski theorem also characterizes what happens when you have equality. And what this implies is that these two convex bodies are homothetic. That's the word they use. And what does that mean? There exists a transformation T from R to D to RD, and a fine transformation, which is of the form T of X is Cx plus gamma, where C is a positive real number, such that T of delta phi 1, 0 is equal to delta phi 0, 1. Okay, so now it turns out that we have just enough information about these sets. First off, we know their volumes. So that we get from that this number C over here is equal to this ratio of the d roots of their volumes. And now to get the gamma equals 0, the translation to be 0, we use the fact that these delta phi 1, 0 and delta phi 0, 1, that when you rescale by C, and then you cut with you cut with that hyperplane, that H minus, the stuff above it, you get exactly the same thing. So you have this compact set contained in this hyperplane, and when you have to translate then by something in the hyperplane, but since the set is compact, the translation has to be by 0. Okay, so now that we have this, we can go on, and we remember that we started with the valuation mu something another, where mu was any m valuation. So if I were to look at this delta 1, 0, and then I project onto the first axis, this is actually going to give you the gamma u d1. So the point, which is the point, the smallest mu value that you can get for this delta 1, 0, that's going to be gamma u d1. Okay, and of course the same thing for delta 2, 0 gives you gamma u d2. So what one does then is one takes mu is equal to mu ej for the different j's, and then one gets a statement that from this, we get these statements, these things being equal, since we get delta 0, 1 by multiplying by C. Okay, which is the ratios of these d roots of these multiplicities. So this implies the first statement of the theorem F, which was saying that these the ratios of this gamma ej are the on d2 and d1 are the same. And in fact, the first part of the second half, but we don't get the fact from this that they're rational numbers. That's another argument. Okay, so I guess I have this is a good stopping point. So I'll stop here. I'll go maybe back to the statement of theorem F. Yeah. Okay. So I will stop here.
Okay. Thank you, Dale. Are there any questions?